Okay, good morning.
Good morning.
Okay, this is chapter 10. Almost all the programming details, the formula, the detailed formula that you need to program is in this chapter. Okay, so last lecture we derived the formula in matrix form, but some of the details are not given yet. Okay, so this chapter will focus on details. First, let's talk about the finite element statement. Well, is the 1D, 2D, and also 3D elements. Okay, in 1D, it is a line element. We could have two nodes, which means the displacement field will vary linearly between the two nodes. We could also use a three-node element. So there's a mid-edge node here. If we use the three-node 1D element, it will be quadratic. Okay, so this is linear. This is quadratic. 1D. And then 2D. For 2D case, we could have different shape. One is the triangular shape. Okay. For the triangular shape, we can have a three-node element like this. We can also have six-node element. Yeah. And again, the three-node element, because along the edge, things can only change linearly when the two locations are known, right? And that will be a linear element. For this one, along the edge, you have three node positions. Passing these three nodes, you can do a quadratic fit. So this again is quadratic elements. But because it's 3D, we can have also quadrilateral element, which is like this. So we can have four-noded element. We can also have a-noded element, where you have four corner nodes and also three mid-edge nodes. And sometimes you can also add one more node in the center of the element. Then you will have a nine-noded quadrilateral element. Okay, so that's the 2D case. Similarly, we can extend the idea to 3D. Then you could have a tetrahedral element like that is like a pyramid. You have four corners and add four nodes there, so you have four corner nodes. You can also have quadratic tetrahedral element where you have this mid-edge node here, 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 here. So this again is linear, and this is quadratic. You can also have brick element, which is the equivalent of the quadrilateral element, like this. For the brick element, you can have all corner nodes, so that will be an A-node brick element like this. And again, this will be linear. You can also add the mid-edge node. So you have all these corner node, and then plus those mid-edge node. And if you count it, there will be, I believe, 20 nodes. This is a 20-node brick element, and again, the variation of the displacement is quadratic. When I write these orders, you need to be aware that when I say linear, it refers to displacement. Then the strength is one order lower than that, because strengths are derivative of the displacement. So these can only represent constant stress. This is linear, constant strain and stress, constant strain and this is linear strain and stress. Similarly, constant strain and stress, linear strain and stress. Okay, and of course, usually if you allow linear variation of the stress, the accuracy is higher, is much better. Okay. Well, for this course, we're not going to do all the elements. We will just select one that that will enable us to model a linearly varying strain and stress field. So we will select this one. Okay, this is a 8-noded quadrilateral element. So this is the recorded 8-noded quadrilateral, or simply Q8. In many commercial FEM code, is called Q8. All right, if we do that, what will be the shape function? Let's derive this. When I draw it like this, it is in the global coordinate, so it may not be regular in shape. When it maps this into the natural coordinate, it will be a regular, actually a square, because here will be from -1 to 1, and here will be also -1 to 1. It's a very regular square, okay? And then let's draw that and then derive the shape function for the Q8 element. In natural coordinate, this is theta, this is eta. It is a square of size 2 by 2. We have 8 nodes here. Theta from -1 to 1, eta from -1 to 1. We named it this way. This is 1, 2, 3, 4, 5, 6, 7, 8. So that's how we are going to name the node of the element. And with this naming convention, we can show that the shape function will be as follows. N1 is equal to -1/4, 1 minus theta, 1 minus eta, theta plus eta minus 1. Okay, and the N2 is equal to 1/4, 1 plus theta, 1 minus zeta, eta minus zeta minus eta minus 1, and then n3 equals 1 over 4, 1 plus zeta, 1 plus eta, zeta plus eta minus 1. And then n4 is equal to negative a quarter, 1 minus zeta, 1 plus zeta, eta minus zeta minus eta plus 1. And also n5 is equal to half 1 minus zeta squared, 1 minus eta. And 6 is equal to half 1 minus eta squared, 1 plus zeta. And 7 is equal to 1 half 1 minus zeta squared, 1 plus eta. And n8, so this is n7. It's equal to half 1 minus eta squared, 1 minus zeta. Okay, that's all the 8 shape functions.
N1 in the textbook is zeta plus eta plus 1.
Let me see. Oh yeah, that should be plus. Yeah, thank you. Well, you may ask, it looks complicated, or at least how can you remember all this? Well, it's difficult to remember, so you can refer to the textbook. But there's one way that you can actually derive that quite easily. Okay, I'm going to show how to do that. Okay, before we try to derive that, let's discuss the property of the shape function. We actually, for 1D case, we talked about that before, and also actually for 2D. It turns out the shape function must satisfy two properties of a shape function. First, for node I, if you plug in the coordinate of node J, okay, into the shape function, it should be either 0 or 1, depending on whether J coincides with I or not. And that property is called delta ij. When I is equal to j, delta ij is equal to 1. That's called the canonical delta. We can also write it as this, which is 1 if I is equal to j. It's 0 if I is different from j, okay? So that's one property. What does that property mean? Because we use shape function to interpret a field, and the interpolation is from nodal displacement, right? We select a 8 node. We assume the displacement at these nodal positions are known. Let's say at this point, the displacement will be u1. Okay. Now the interpolation function is equal to displacement is equal to the shape function times the nodal displacement. Now, if I express that in a matrix form, it will be like that. Therefore, at that location, the displacement is u1. Okay, so this should recover that value, right? The displacement at that point should be equal to U1. So if you put it there, that means U1, and then this is the shape function, which is N1 plus whatever value at node 1 plus times U1 plus N2 at node 1 times U2, etc. up to 8. N8 at node 1 times U8. This is the definition of the interpolation. Okay? So it's N1 times U1 plus N2 times U2 plus up to N8 times U8. And inside is the position, the variable is the position coordinate. Now we let the position to be node 1. So this should be node 1 and node 1 and node 1. We also know that these two should be equal, right? They are the same thing. So this is N1, this is N1. So the only thing for these to hold true is that this should be 0. So the rest of the contribution should be 0, and that should be 1. Okay? This is exactly that property. Okay, so this is to ensure reproduction of nodal displacement values. Okay, so this is the first property that any shape function should have. It means when it is a shape function for node I, when the coordinate is node j and j is different from I, it should be 0. When j is the same as I, you are now standing at the location of that shape function, it should be 1. Second property is that when you add all the shape functions, for one element there are a total of 8 nodes. So it adds it from 1 to node. For any location, okay, it should be equal to 1. What does that property mean? Well, your displacement is equal to this, right? So any displacement is equal to the shape function times that nodal displacement, add them together. Now, if we let the displacement to be a constant, so this whole thing, there's no deformation, just move 1 unit, for example, or any unit, any value. Let U is equal to C, which is a constant. When the element have a constant displacement, all those nodal values, U1 up to UA is equal to what? Is equal to the same value, C, right? Okay, so this is equal to C. But this displacement is also a constant. So it means C is equal to summation Ni times the nodal displacement, which is also C. The summation is from 1 to 8. Well, C is same constant, they just cancel. Therefore, 1 is equal to summation I is equal to 1 from A, and then and shape function I. Right? Therefore, if you have a shape function, you add them all together, it should give you unity. This enables the interpolation function to be able to reproduce a constant stress field exactly. If it's not 1, you won't be able to reproduce a constant stress field. If any interpolation that you propose cannot even reproduce a constant field exactly, it's not going to work. The accuracy will be very, very poor for any other field, right? So at least it should work exactly for a constant field. That's what this property is for. All right, and if you check this shape function, check these two properties, they satisfy. If you add all these together, they are equal, the sum of it is equal to 1 exactly. And you put in each location here, at this location, first one is equal to 1, the rest is 0. At the second location here, second expression is equal to 1, the rest is 0. Okay? And still, how can we reproduce that, derive these expressions fast? It turns out there is a formula. You can use a formula in the following form. The shape function of node I is equal to the multiplication of 3 line equations. So it's 3 lines, the equation that represents 3 lines passing other nodes. But I. And put an adjusting parameter in front. What does that mean? Okay, let's use an example to illustrate that. Let's say we want to derive the shape function for this node. Okay, we need to draw 3 lines to pass all other nodes, but not this node. How are you going to draw 3 lines that will pass all the nodes? Okay, let's say if we draw 1 line here that passes 3 nodes, another one here, then the third line will not work because it passed that node, right? Okay, any other plan?
One across the top,
One across the top,
one at Jada equals 1,
this one.
and a diagonal line between each.
Very good. Okay, so you can draw this line, and this line. Now, all the 3 lines will pass all other nodes but this one. That's the only way that will work. If you draw this, you will need 4 lines. So this one you can draw 3 lines. All right. For this line, what is the equation for this line? This is a vertical line.
Yeah.
So the x-coordinate is equal to 1, right? So theta is equal to 1, or theta minus 1 is equal to 0. The top line is a horizontal line. Eta is equal to 1. So eta minus 1 is equal to 0. This one is at negative 45. And its equation is like this. Theta is equal to negative eta, and you pass negative 1. So if you use the intercept equation, that equation can be written as this. And this one, you move everything to the left side, or theta plus eta plus 1 equals 0. Okay, now we have these 3 equations. We have this one, and this one. Therefore, according to the formula, n1 is equal to a constant times the equation for 3 lines. So the first one is eta minus 1. This one is theta minus 1. This one is theta plus eta plus 1. Okay? And you compare that. That's what you have here. And of course, 1 minus theta or theta minus 1, you flip the position, it make no difference. And then to determine C, you let theta equals that point. At that point, theta is negative 1. Eta equals negative 1. When you put negative 1 as theta and also negative 1 for eta inside, plug that in. The whole thing should be equal to 1, the delta property. And with that, Ni should be equal to 1. Okay? And this is 1. This will be -1, this will be -1, and plug everything in. You can solve for C, and C turned out to be -1/4. Okay, that's how you derive that. Therefore, now C is null, and I is equal to -1/4 eta minus 1, zeta minus 1, eta plus zeta, zeta plus eta plus 1. Okay? So that's the derived formula. Which is exactly that one. And of course, once you know how to derive for this corner one, you can do the same for this one, and that one, and that one, okay? Now, let's pick a mid-edge one, this one. For the blue node, now we also need to draw 3 lines that pass our other node, but this one. How do you draw it?
One on the left, one on the right, one at the top.
If we draw this one here, and that one there. And again, write out the equation that represent this line for that line and that line. Move everything to the left. You have 3 expressions. Times them together, put a constant in front, and then you let the coordinate to be that point, and you know the shape function must be 1. And use that to determine that constant. And at the end, you will get this expression. Okay? Expression N5. All right. Okay, that's how to derive this formula. When the first person that came up with the shape function, I think he thought that it is good luck that we can find a shape function like this very easily. So he named that element serendipity. So serendipity means luck or something, right? So that's also called serendipity element. So that's where that name is from. All right, now we know the shape functions. Let's now derive the details of the element stiffness matrix. Okay? Well, the shape function works in this way, okay? Element stiffness matrix. For U, it is in this Ni and then U A I, like that. And V will be similar, VA and then I, okay? Because in 2D problems, the displacement is 2D, so we have an X component, which is U, and a V component, which is the Y component, which is V. In matrix form, we write it this way. We can write it U and then V, and then we have N1 here and then 0, N2 here, 0, okay, up to N8 and then 0. Here we will have 0, N1, 0, N2, and then 0, N8. All right, the nodal displacement vector, instead of a column of 8 by 1, it will be 16 by 1, because the first position we have U1 in x direction, and then we have v1 in y direction. So we have u1 here, v1 here, and then u2 here, and then v2 here, up to u8, v8. This is the nodal displacement, okay? And as you can see, this is a component 2, a 2-component column. This is long, okay? It is 2 by 16. This is 16 by 1. At the end, you should have, when you have a matrix that is 2 by 16 times a vector that is 16 by 1, at the end, the row will be determined by the first number. The column will be determined by the last number. So at the end, this is 2 by 1, like that. So it is consistent. Okay? All right. Then we know that ipsum x, the displacement by definition is equal to partial u, partial x. We actually derived this before. Okay? So the operator partial over partial x will be act on n matrix only, because as far as the differentiation is concerned, these are constant. So these will act on that. Okay? And also ipsum y is equal to partial v, partial y. And then gamma xy is equal to partial u, partial y, plus partial v, partial x. And then take the expression u, put in here, and the expression v, and put in here, and put in both. Then we can express the strain component in the matrix form. We would like to write it as, again, a column vector. Therefore, we have ipsum x, ipsum y, gamma xy in the following form. The first one is partial n1, partial x, and then 0. And the third column is partial n2, and then partial x, etc. Up to the 15th position, partial n8, partial x, and the 16th position is 0. Right? And here, correspondingly, we have this u1, v1, u2, v2, up to u8, v8. And you check, when you take this row and times the column, you get exactly that. Okay? And the second one, this is 0. This is partial n1, partial y, 0, partial n2, partial y. This is 0, and then partial n8, partial y. And again, the second row, finish the multiplication, you get exactly that. And the third one is a little bit complicated. It has non-zero across every column position. Is partial n1, partial y, partial n1, partial x, then partial n2, partial y, partial n2, partial x, etc. up to partial n8, partial y, partial n8, partial x. Take the third row and times corresponding thing and then add them together, you get exactly that. Okay? So this is the important result where the displacements are expressed in terms of nodal displacement. The strings at an arbitrary point, at any point, is expressed as a big matrix. We call it B matrix. So this is called the B matrix. And then times the nodal displacement vector. Okay? All right. all this is very good. However, if you look into the expression here, this is the first shape function, a derivative of this first shape function with respect to x. But we like to express shape function in terms of theta and eta in natural coordinate. So you cannot directly calculate that. We will need to know the relationship between x, y, and theta and eta. How to do that?
Jacobian.
We use Jacobian, we use the same shape function, remember? So we assume from the natural coordinate to the global coordinate, the shape function is also the n shape function. So we use the same, shape function to interpolate x and y from theta and eta. Remember, the shape function was first introduced for interpolation of displacement. But because we also need to know the relationship between the natural coordinate and the global coordinate, we also need some kind of interpolation. And then the idea will be, why not use the same interpolation scheme? So one is for position, the other one is for displacement, same interpolation scheme. So if we do that, that means x now is equal to sum and then ni and then theta I is from 1 to 8. Okay? Now this time, these theta I are the natural coordinate nodal positions. These ni are the shape functions. Okay? And therefore, partial x, partial theta is equal to partial n1, partial theta, and then theta 1, plus partial n2, partial theta, and then theta 2, up to partial n8, partial theta, and then theta 8. Okay? Oh, I'm sorry. This one here, it should be, the nodal positions are actually in global coordinates. So it's x, not theta, I'm sorry. So it's x1, and then here is x2, and then here is x8. Okay, like that. Similarly, partial derivative of y with respect to eta is equal to partial n1, partial eta, and then y1 plus partial n2, partial eta, y2, etc., up to partial n8, partial eta, and then y8. Okay? And then the relationship between n1 and n theta is this. Partial n1, partial theta is equal to partial n1, partial x, partial theta, plus partial n1, partial y, partial y, partial theta. This is the so-called chain rule. Okay? On the left side, we view the function as n1 as a function of theta. But we know that n1 depends on both theta and eta. Okay, and then theta and eta, and there is a relationship between x and y and theta and eta. Therefore, when we do the derivative of a function with respect to that, because n1 has a dependence on x and also y, therefore, the derivative with respect to eta is equal to this intermediate function of 1, which is this one, plus a second dependency of y together. So this is the chain rule. Similarly, we can say n1 of theta, and with respect to eta is also n1 and then partial x, partial eta plus partial n1, partial y, and then partial y, and then partial eta. Okay, this is y. With that, you can write it in matrix form, partial n1, partial eta, partial n2, partial n1, partial eta is equal to this partial x, partial theta, partial y, partial theta, partial x, partial eta, partial y, partial eta. And then this is partial n1, partial x, partial n1, partial y. Okay. This expression using the chain rule, this is in individual form. The same expression is expressed in matrix form. So these two are completely equivalent. Okay? But when you write it in matrix form, there's advantage of that. Now you can say that now you can express, we call this the Jacobian matrix. Okay? With the Jacobian matrix, now you can say partial n1, partial x, partial n1, partial y. Is equal to Jacobian, the inverse of the Jacobian, if you invert that and put it on the other side, times partial n1, partial theta, partial n1, partial eta. Can we box that? The significance of this expression is that now you can really calculate these two things. Okay? Before here, you don't know because n1 is an implicit function of x and y. It's an explicit function of theta and eta. When it is an explicit function of theta and eta, you can do the derivative very easily. Implicit function is difficult. That's why we need to go through that, okay? But once you do the derivative explicitly, and then here, you can also do it using the expression here. Partial x, partial theta is this. And as you can see, all the derivative here, you can do it explicitly because n is expressed as a function of theta and eta. So all these are doable, okay? So when you express that, everything here can be done. Here can be also done. This is what we want, so we invert it. So that is why this is from, okay? So with this and that together, these two things together, you can now calculate the matrix B. Every element should be doable, okay? So that's the significance of that. Okay, so at this point I can say with these three matrices A, B, C, with A, B, C, you can calculate the B matrix explicitly. Okay? because all the expressions in A and B on the right hand side are explicit. So you can calculate that. Once you do that, then you have matrix B. Now, because I need a space, I need to erase this. Then, remember we have this B matrix. The stiffness matrix is B transpose, and then D matrix, and then B. D is the material matrix. And then we talk about plane stress and plane strain. So, now, let's see the material matrix. Oh. This should be material matrix. For 2D, I mentioned last time in previous lectures, you cannot really have truly 2D or 3D situation for elasticity problem. The only way you can have a true 2D or 2D case or 1D, I'm sorry, you cannot have a true 2D or true 1D case for elastic problems because of the non-zero Poisson's ratio, right? If the Poisson's ratio is not zero, when the stress is 1D, strains are 3D. When the stress are 2D, strains are also 3D. Okay? Therefore, we need to distinguish plane stress and plane strain. So, plane strain, the D matrix is this. We linked sigma x, sigma y, and tau xy, or sigma xy z, same thing, tau xy z, is equal to E over 1 plus nu, 1 minus 2 nu, then 1 minus nu, 0, 0, 0, 1 minus nu, 0, 0, 0, 1 minus nu. Epsilon x, epsilon y, gamma xy. Okay, this is the D matrix. For plane strain. And to be complete, you need one additional expression that is for out of plane stress, sigma z. Sigma z is linked to sigma x and sigma y in this way. Okay? So you really have, for plane strain problems, you have 4 stress components, not 3. You have this in-plane component plus a out-of-plane thickness normal stress, which is usually not 0. Okay? All right, for plane strain, for plane stress, now the relationship is this: sigma x, sigma y, sigma xy is linked to E over 1 minus nu squared, and this is 1 nu 0, nu 1 0, 0 0, 1 minus nu over 2, and then epsilon x, epsilon y, gamma xy. Notice that we always use the engineering shear strain. I explained that before, not the tensorial shear strain epsilon xy. Epsilon xy is just half of gamma xy. Okay. And then with plane stress, the non-zero stress components are 3. That is fine. But the strains are the non-zero component for strains are 4. Okay. So this one, sigma z is 0. Here I should write it, epsilon z is 0 here. And this one, sigma z is 0. However, epsilon z is not 0, okay? And I believe epsilon z is equal to negative mu over E sigma x plus sigma y. Okay, and that is in general not 0. Alright, let me write that. This is D matrix for plane strain. This is the D matrix for plane, write it here. D matrix for plane stress. And it's very important to denote which the situation here. One is for plane strain, one is for plane stress. And the expressions are different. Okay? And also don't forget the thickness situation. For plane stress, thickness stress is 0, but thickness strain is not 0. For plane strain, the thickness stress is non-zero, and the thickness strain is 0. Okay? All right, at the end here. Now we have the B matrix, we have the D matrix. We can now write the element stiffness matrix, okay, E, which is this. B transpose D matrix, and then B matrix, and then dV integrate over element E. Right? So that's the original formula in global coordinate. Now we need to translate that, we need to transform that into natural coordinate. So dV is 3D. 3D in 2D case means dx dy times the thickness. We assume thickness is t. So t is a constant, we take that out. And the integration is 2D, okay? So now B transpose is the same, D and then B, and then the Jacobian, determinant of the Jacobian, and then d theta, d eta. And the limit is from -1 to 1, -1 to 1. So it's very important to remember this. Okay? With that, now we put in the expression we derived earlier for the B matrix, -1, -1 to 1 to 1. The B matrix is this. Now we transpose it. Initially, the B matrix is 3 by 16. So it is a short and long, it is a narrow and long matrix. But when you transpose it, it becomes this. This is partial n1, partial x, and then 0, partial n1, partial y, 0, partial n1, partial y, partial n1, partial x. Okay, here. Okay, let me write the second one also. Then partial n2, partial x, 0, partial n2, partial y, partial 0 here, partial n2, partial y, partial n2, partial x, up to partial n8, partial x, 0, n8, partial y, 0, partial n8, partial y, partial n8, partial x. Okay, this is the B transpose. And the D matrix is here or there, depending on which situation, plane stress or plane strain. And then times the B matrix again. The B matrix this time is 3 by 16. So partial N1, partial X. 0, partial N1, partial Y. 0, partial N2, partial Y. Partial N2, partial X. And then partial N2, partial X. 0, 0, partial N2, partial Y. Partial N2, partial Y, partial N2, partial X, etc. And the last one, I don't have enough space here, so partial N8, X, and then 0, partial N8, and partial Y. And then here will be 0, partial N8, partial Y. This one. And then partial N8, partial Y, partial N8, partial X. Jacobian d theta d eta. Okay? Alright, let's mark the dimensions here. This matrix is how much by how much?
16 by 3.
So 16, the rows are 16 by 3. This one,
3 by
3 by 3. Very good. And then this one,
3. 3 by 16.
3 by 16. And this thing is a number, is a determinant. Okay, so the end result is these should be what? The dimension for this one?
3 by
Check.
16 by 16.
Take the first one and take the last one. So it's 16 by 16. Well, we have, for one element, we have 8 nodes. But why the stiffness matrix is double the size? I mean, it's 16 by 16, not 8 by 8. Why?
We have an X and Y displacement.
We have 2 degrees of freedom for each node. We have U and V, okay? Therefore, each node has 2 degrees freedom. Total 16 degrees of freedom. So it's 16 by 16. All right, I think it's almost time, so I will stop here. But at that point, if I ask you to start to program it tomorrow, just the element stiffness matrix, you should be able to do it. Because every element, every coefficient here is known. Okay? You have all the formulas. You have explicit formulas for each coefficient in this matrix. So the only thing you need to know is you definitely need to know how to program a function that perform one matrix times another matrix. Arbitrary dimensions. The first one should be n by m. The second one should be m by p. So these m and p and n can be anything, any integer. Okay. Apply. So once you use that, you repeatedly call that. You can, for example, these times that you call the function once and put in those. You get one matrix, and then you call the function again with that matrix times that matrix, things like that. Okay. Prior to that, of course, you need to know how to calculate that coefficient, and all the formulas I explained this lecture will be useful. Okay, and then remember the big statement. We have the K stiffness matrix, and then we have the contribution for the body force, the contribution from the traction, and the contribution from prescribed or essential boundary conditions. So we have 3 additional things on the right-hand side of the equation. We're going to talk about that next lecture, but it will not be long. It will be like a 30-minute lecture for next time, and then you're done. You have all the necessary formulas and knowledge.